next speaker is Marc-Oliver Pohle, and he will speak on score-based calibration testing for multivariate forecast distributions.
Yeah, thanks, Johanna. Yeah, thanks for giving me the opportunity to give this talk here. And this is joint work with Malte Knüppel from Deutsche Bundesbank and Fabian Krüger from Karlsruhe Institute of Technology. And as Malte is working for a central bank, the following disclaimer applies. So the views expressed here are not the ones of the Deutsche Bundesbank or the Euro system, but by the authors alone. Okay. So Johanna perfectly motivated in her talk on Monday what we are doing. So she even had a slide on multivariate calibration, and this is exactly the setting we are in. So we have the variable of interest is multivariate. So I'm also an econometrician, so inflation and interest rate and GDP growth, or several financial returns, or several meteorological variables that we want to forecast, and we want to forecast the forecast to be probabilistic, so we want to forecast the whole probability distribution. And the simple question that we want to answer is if the forecast distribution that we issue, or that a certain method issues, is calibrated. And in the univariate case, I would say calibration testing for probabilistic forecast is standard in many disciplines. There you take the probability integral transform, so apply the forecast distribution to the outcome and check its standard uniformity, either by looking at a histogram or the CDF, or applying a formal test for uniformity. And there the null hypothesis would be called probabilistic calibration, so that's just PIT uniformity. And the question is, does this approach readily generalize to the multivariate case? The answer is no, because there is no multivariate analog to probabilistic calibration really. So that's a problem. And even though this is the case, there is a literature on that, of course, that tries to somehow take the testing for PIT uniformity to the multivariate case, and there are quite different strands of the literature in econometrics and in meteorology/statistics. So the econometrics literature uses the Rosenblatt transform, so essentially factors the conditional, the joint CDF into conditional CDFs, and checks standard uniformity and independence of this of the PIT values of these conditional PIT values. And there are several problems with these tests, and the major one is that the tests depend on the ordering of the variables that you choose in the Rosenblatt transform, and this has recently been solved in a paper by Dovan and Manna, which propose order invariant tests, but there remain several problems because their tests are limited to small dimensions and closed form distributions. So if you have a distribution from an MCMC sample, like you most often have in practice, I would say, you can't really apply these tests. And on top, they are not interpretable. And so what I like much more is the approach in the meteorology and statistics literature. They somehow focus on graphical diagnostic checking and apply the so-called pre-rank function approach. Thordis and Johanna have contributed a lot to this literature, and this approach tries to reduce the dimensionality from D, so high dimensional, so multidimensional, to 1 by applying a function somehow involving ranks. And the problem we find with this approach, the pre-rank functions that are used in the literature have somehow low power, so only power against certain alternatives, so they will not be powerful in a calibration test usually. And we generalized this pre-rank approach in our paper, so we set out from there. So what we do, First thing is we introduce a general framework for calibration testing for multivariate forecast distributions. And the nice thing is that even though it's simple, it encompasses the econometric approaches as well as the statistics approaches. And yeah, so unifies an interdisciplinary literature. And what is more important, it uncovers implicit choices made in the tests in the literature, and allows for the construction of yeah, more powerful tests, more powerful diagnostic procedures, I would say. And it allows for statistical tests as well as graphical diagnostic checking. I think that is important because a statistical test says you if you're calibrated or not, if the method is calibrated or not, but not in which direction you can improve. Okay, and second thing, we propose new tests or diagnostic checks building on proper scoring rules. Okay, so the general framework in a way. First thing is, yeah, what do we want to test? And we take the null hypothesis of auto-calibration that has appeared several times during this week. So this just means the forecast distribution is auto-calibrated if the conditional distribution of the outcome vector given the information in the forecast distribution is equal to the forecast distribution. Okay, and this is somehow, I would think, the most natural null hypothesis that you could want to test. And second example is that it generalizes readily to the multivariate case and implies probabilistic calibration in the univariate case. Okay, so the framework for testing, the general framework is very simple. So we found out that instead of a function involving ranks as this pre-rank function approach, you can choose any function of the forecast distribution and the outcome to reduce the dimensionality. So this maps the forecast distribution and the outcome vector to the real line, this function. We call it dimensionality reduction function. And then it is useful to think about it in this way. You consider an auxiliary univariate forecasting problem where you just try to evaluate if this function is calibrated. Yeah, and so this is in a way the realization, and you also have the forecast distribution which we call capital G, because if you have the true forecast, so the original forecast distribution, the multidimensional one, you can compute the implied forecast distribution for this dimensionality reduction function. Okay, and then you simply can apply a test for univariate calibration. And yeah, second step is choosing a testing principle. So the first one is the classical one. We just test PIT uniformity, so probabilistic calibration of this auxiliary forecasting problem. And the second one, which I won't discuss here, is just testing unbiasedness of this auxiliary forecast in this auxiliary forecasting problem. It is a little bit less powerful, but in terms of interpretation, it's quite nice. But I won't have time to discuss it today. Okay, so how do we implement the test in case A? So it's simple. Just compute the PIT values of the auxiliary forecasting problem, and this is like in the univariate case. The only thing that's a bit different, usually you can't compute this forecast distribution, this implied forecast distribution for G. So this in closed form, but you have you can generate as many draws from your original forecast distribution as you want, and you can approximate it arbitrarily well. And then you just compute the PITs and test standard uniformity by some formal statistical test for it, or look at the at the histograms or the CDFs of the PLTs. Okay, the tests have asymptotically correct size under standard time series assumptions. And of course, power is most interesting here. It strongly depends, of course, on the choice of the G function of the dimensionality reduction function. Yeah, and we compare the dimensionality reduction functions from the literature and point out their shortcomings and what would be desirable for them, and ask ourselves, are there better choices for these G functions than the ones in the literature? And if you think about it, such a dimensionality reduction function, yeah, it has to lose information because it reduces the dimensionality from possibly 10-dimensional to 1-dimensional, but it should keep as much information as possible. And the natural choice here is a scoring function, or a scoring rule, a proper scoring rule. So we set in the second part of our paper the dimensionality reduction function to a scoring rule. Yeah, the reason for this is, as I said, the scoring rule should keep as much information as possible while reducing the dimensionality naturally. And there are some more reasons for choosing scoring rules, but you can't really give a formal proof that a scoring rule is the optimal choice or so. So it's kind of heuristic, this choice, and there may be better choices. Okay, but the scoring rule approach has a nice interpretation because it, in a way, compares the realized scores that you observe to the anticipated scores by the forecaster. So consider, so X denotes a draw from the forecast distribution, and so intuitively the score-based approach compares the realized uncertainty to the anticipated scores by the forecaster. And so you can, by looking at the PIT histograms, say if the forecaster overestimated or underestimated uncertainty. So this is really a test that takes into so that looks after yeah, the uncertainty if the uncertainty is assessed correctly by the forecaster. And this, of course, can yield valuable feedback for model improvement. Okay, you can choose any multivariate proper scoring rule. So if f comes in the form of a density, then the log score is a natural choice. And so if not, as usually in practice, as I told you, the forecast distribution in the multivariate case comes in form of an MCMC sample, or in meteorology in the form of ensemble forecasts. Then you can choose, for example, the energy score, which is usually a little less powerful as we find in simulations, but is universally applicable. So yeah, that's the two choices we consider in the paper. And here's an example, a very simplistic example. So the true DGP is bivariate Gaussian and IID, and the forecasts are also bivariate Gaussian and IID, but as you see, the variance is too low. The true covariance matrix is twice as large as the predicted one. And this you see in the PIT histogram when using the log score. So the true uncertainty, the realized scores are usually much bigger than the forecasted scores, and this is why they fall into the upper regions of the forecasted scores, of the distribution of the forecasted scores so often, and the PIT histogram is not uniform. Okay, the simulations show that the PIT test is well sized, and it has good power in detecting different forms of misspecification, so wrong variance, wrong correlation structure, wrong type of distribution, and so on. Using the log score, it performs as well as this Dovan-Manna test, which is only applicable, as I said, in restricted situation. And using the energy score, it has a little less power, but is universally applicable. And the approaches from statistics and meteorology don't have so much power. Okay, quickly, an application, a macroeconomic application. So we consider forecasts coming from a Bayesian vector autoregressive model, and it's a trivariate system, so forecasts for GDP growth, inflation, and the T-bill rate. And this model, this Bayesian vector autoregressive model, has time-varying parameters and stochastic volatility to accommodate for the ongoing structural change in the economic time series. And calibration of this model, so this is a workhouse model in economic forecasting, and calibration of this model is not rejected, but if you take away the time-varying parameters and the stochastic volatility, so use the corresponding B-val model with constant parameters, then calibration is clearly rejected with the energy or the log score. And yeah, let's look at the graphical diagnostic tools. So for the stochastic volatility model, so the time-varying parameter and stochastic volatility model, the histogram is pretty uniform of the score PITs. And also, if you plot the PITs over time, so they look pretty uniform over time. And with the constant parameter model, you see an interesting pattern. Uncertainty is too low in some instances and too high in others. So this is why this U-shape occurs. And you can see this nicely in this plot of the PITs over time. So during the 70s, the uncertainty in the model that the model predicted was too low. So many high PIT realizations. Then during the Great Moderation, the uncertainty was much too high that the model predicted. So and so on. So you can see a lot in the diagnostic plot, I would say. Okay, we also have a finance application, which is more high-dimensional and non-parametric, but I will skip this. And yeah, just give a conclusion. So we introduce a general framework for testing calibration of multivariate probabilistic forecasts, which unifies the literature and allows for the construction of new tests. And yeah, our tests have some advantages. They are powerful, they are universally applicable. So in high dimensions for forecast distribution coming in various forms, for example, from MCMC samples, they are somehow interpretable in terms of this forecasted versus realized uncertainty. And most importantly, they are simple and easy to apply because we know we use known tools, so already in the toolkit of forecasters, so the PIT histograms and scoring functions. Okay, and there's a nice complementary paper by Sam, Johanna, and David, which is complementary in the sense that they propose specific pre-rank or dimensionality reduction functions that tell you that are not that powerful in general, so if you want to test calibration in general, but that hint you better in the direction of the form of misspecification. So is the mean misspecified, is the variance misspecified, is the correlation structure misspecified? Okay, so if you're interested, you can ask me questions, but the preprint and the R package are available online. So thanks a lot.
Maybe one quick question for Mark, yes?
In the univariate case, I think we could apply your method instead of just the ordinary pit value method. Would there be any advantages to doing that, do you think?
We thought about it in the beginning, but then we didn't think about it anymore. But it has been applied by some economists in this context, and I wondered why, but I didn't. I mean, yeah, so we can talk about it, but I have no satisfying answer. The question is, why would you want to apply it? Because, yeah, but yeah, maybe let's talk about it later.